So we saw that the limit of compact operators is compact, and therefore since every operator with finite rank is compact, the limit of operators of finite rank is compact. Now the question we wanted to ask is that is any compact operator the limit of operators of finite rank? This is not generally true. So, but here is a situation where it is true. So, proposition, let V be Banach and W a Hilbert space. So, the range space is a Hilbert space. Okay. Let T belong to K of VW, that is, it's a compact operator. Then T is the limit of operators of finite rank. So proof. So B closed unit ball in B and K equals T of B closure. So this is compact. So let epsilon be greater than 0 and let Fi in W, I in I, finite indexing set such that K is contained in union I in I, BW, this is the ball in W, center Fi and radius say epsilon. Okay. Let G be the span of F1, Fi, I in I. So these are finitely in number. We don't know about its linear independence, but definitely this implies that dimension G is finite. Okay. So, and let P from W to G the orthogonal projection. So dimension G is finite implies G is closed, and therefore P from W to G be the orthogonal projection. Then P composed with T is of finite rank. Because T takes V to W and P takes W to G. G is a finite dimensional space, therefore this is a finite rank. So now you let X belong to B. Then there exists I naught in I such that norm of Tx minus Fi naught is less than epsilon. Okay. Then norm of P composed with T at X minus Tx minus Fi naught is equal to norm of P composed with T at X minus P of Fi naught, because Fi naught belongs to G and therefore P of Fi naught equals Fi naught. Okay, so that is the reason. So now norm P being an orthogonal projection, norm P is equal to 1 and therefore this is strictly less than epsilon, because this is okay, norm P is equal to 1. Normally a projection will have norm bigger than or equal to 1 and here we have an orthogonal projection, therefore it's so this implies that norm of P composed with T X minus T of X is less than 2 epsilon for all X in B, and this implies that norm of P composed with T minus T is less than 2 epsilon. Okay, so this completes the proof. So we can approximate every the compact operator for given any epsilon by an operator of finite rank, and therefore you have that it is the limit of operators of finite rank. So let us, here's an example. So let K belong to L2 of 0 1 cross 0 1. Let F belong to L2 of 0 1. Define capital K of F. So it's a function, so its value at t as integral 0 to 1 K of St Fs K of Ts, if you like, doesn't matter. Okay, so this is like a similar operator we defined in the C01. So now we are defining it in L2. Okay, okay. So now we have integral 0 to 1 Kf of t square dt is integral 0 to 1 dt. Okay, so mod 0 to 1 K of Ts Fs ds square, and now I am going to apply the Cauchy-Schwarz inequality there. So that's 0 to 1 integral 0 to 1 K Ts ds square into integral 0 to 1 mod Fs square ds and then dt. Okay, so that is equal to norm F square in L2 and integral 0 to 1 integral 0 to 1 mod K of St or Ts square ds dt, and that is of course finite, and this implies that capital Kf belongs to L2 of 0 1, and in fact norm of Kf in L2 is less than or equal to norm K in L2 norm F in L2. Therefore norm K is less than or equal to norm little k in L2 of 0 1 cross 0 1. Okay, so that is the norm here. So now let phi n be an orthonormal basis. We have that because we are in a separable Hilbert space, and for L201. Then you define phi ij of Ts is phi I of t, phi j of s. Okay, and then you have, we have seen this as an exercise. This implies phi ij belongs to n cross n is an orthonormal basis for L201 cross 0. We have done this exercise already. Okay, so we can write small k consequently as sigma ij equals 1 to infinity k phi ij phi ij. So now you set kn equals sigma ij equals 1 to n k of phi ij phi ij. Okay, so then norm of k minus kn in L2 0 1 cross 0 1 goes to 0 as n tends to infinity. Okay, so now define capital K and F of t is equal to integral 0 to 1 Kn Ts Fs ds. So let us see what it is. It is sigma I equals 1 to n integral 0 to 1 k phi ij and phi j of s ds phi I of t. So you have again, sorry, integral 0 to 1 sigma j equals 1 to n phi j of s phi I of t. Okay, so we have this, and then Kn takes L201 to L201 as we have already seen, and norm of K minus Kn is less than or equal to norm of K minus Kn in L201 cross 01, and that goes to 0, and further Kn belongs to the span of phi 1 to phi n, and therefore Kn of f implies Kn finite rank. So K is the limit of operators of finite rank, and this implies that capital K is compact. So capital K is called a Hilbert-Schmidt operator. So this is an important class of operators, the Hilbert-Schmidt operators. Okay. Now we have an important theorem. Okay. VW Banach, T belongs to L of VW. Then T is compact if and only if T star is compact. So let us start with T compact. We want to show that T star is compact. So BV closed unit ball in V, and then T of BV closure, which is equal to K, is compact. Okay, and then if W belongs to K, it is limit of elements of the form T times BV, and therefore norm W will always be less than or equal to norm T. So let Vn sequence in BW star, that is the unit closed unit ball in W star. Okay, now define phi n of W equals Vn of W. So Vn is in W star, so you can even write this as Vn W. This is W star W. This is for all W in K. Then mod phi n of W is less than or equal to norm Vn norm W, and this is norm Vn is less than or equal to 1, and this is less than or equal to norm T we already saw. So this is less than or equal to norm T for all W in K and for all n. Okay, and mod phi n W1 minus phi n of W2 is Vn of W1 W2, so this is less than or equal to norm of W1 minus W2. Okay, so this implies, so K is compact and phi n is bounded and equicontinuous family in C of K, continuous functions on K. So by Ascoli, there exists a convergent subsequence. So convergent subsequence means also Cauchy. So in particular, sup. So given any epsilon positive, there exists a n such that KL greater than or equal to n implies sup of mod phi nk of Tx minus phi nl of Tx is less than epsilon. This is for all x in BV. But what is that? That is sup x in BV mod V and K Tx minus V and L Tx less than epsilon. That is sup x in BV mod T star V and K x minus T star V and L x is less than epsilon. So this implies that norm of T star V and K minus T star is less than epsilon. So that implies that T star V and K is Cauchy, implies convergent. And therefore this tells you, therefore for every Vn in W star, BW star, there is a subsequence which says that T star V and K is convergent, therefore T star is compact. Conversely, T star compact. So this implies that T double star from V double star to W star is compact. Okay. So then you take JV from V to V double star and JW from W to W double star, canonical embeddings. So T double star of JV of X so let X belong to BV and V belong to W star. So T double star of JV of X acting on any V, what is this? This is nothing but JV of X acting on T star V, which is T star V acting on X. Okay, this is just the evaluation map, and that is nothing but V acting on Tx. And that's equal to JW of Tx acting on V. Okay, so T double star JV of X equal to JW of TX for every X in BV, and therefore we have T double star of JV of BV equal to JW of T of BV. But BV is bounded set, this is bounded, and T double star is compact, and therefore this is relatively compact. So JW of TBV is relatively compact, JW is isometric isomorphism, and therefore this implies T of BV is relatively compact. And that means T is compact. And that completes the proof of this theorem.